Hello, everyone, and welcome to Online Lecture 15. Today, we'll be talking about a few different topics together. We'll be talking about power, the distribution of means, and confidence intervals. So we're continuing across the bridge from descriptive to inferential statistics. And the next couple of lectures, the bridge might get just a little bit rickety, but hang tight and we'll be safely across on the other side in no time. All right. So what is power again? It's the probability that we correctly reject the null hypothesis. Okay, all right. And how do we increase power? Remember, there are three ways. We can increase the effect size, which is hard to do. We can increase alpha, which we don't like to do. Or we can increase the sample size, and increasing the sample size is the most common way of increasing our power. Okay. So I had promised a little while back that we would talk more about effect size, and we're going to do that in just a moment. We're going to talk a little bit more about the definition of effect size, because we have some understanding of it, but we'd like to really understand this concept more fully. Okay. So what is effect size? It's the amount that the two populations do not overlap. The amount that two populations do not overlap. So if we're looking at this picture right here, we can see this is the amount. This right here is our effect size. That's the amount that they don't overlap. The rest of it they do, but this amount they don't. Okay, right between the arrows. All right. So to increase the effect size, to increase the amount of overlap, to increase the amount of non-overlap, we have two choices. We can increase the size of the effect, which means larger mean differences, or we can decrease the variability, decrease the standard deviation, decrease the differences between people in the same group. So let's look at each of these in turn. Here's effect size. Small effect size, amount of non-overlap is pretty small. Medium effect size for medium non-overlap, and a large effect size for a large non-overlap. So this is really demonstrating making the mean differences larger. Now, if you'd like to see another picture of this, I have this to show you. Once again, look here. The difference between this mean 40 and this mean 50 is about 10. Over here, the difference between this mean 30 and this mean 50 is about 20. So clearly on the right side, we have larger mean differences, and as a result, we have a larger non-overlap. And so we would appropriately guess that this has the larger effect size on the right side. Now, let's look at the standard deviation piece, because that one's a little bit more difficult to understand. Over here, we have a mean of 35 and a mean of 50 on the left side. On the right side, we also have a mean of 35 for the blue and a mean of 50 for the red. So in this case, the difference between the means in both pictures is about 15. No change. Yet, if I asked you which picture has the larger effect size, which shows the larger difference between groups, you'd probably tell me it's the picture on the right, and you would be correct. So why is that? It's not because of bigger mean differences, it's because of smaller standard deviations in the right picture. Notice how much more narrow the blue and the red are in the right picture as compared to the left picture. Well, that narrowness means we have a smaller standard deviation, smaller spread, Smaller spread in our blue, smaller spread in our red, and that is producing a greater amount of non-overlap. Okay. So now that we talked a little bit about power and effect size, I want to turn to our second topic, which is the sampling distribution of means. Now, so far we've talked about population and sample distributions. But the sampling distribution of means is another type of probability distribution. And it's the third type of probability distribution, really, that beyond population sample and sampling distribution of means, these are the big three that we're going to be focusing on. So for the sampling distribution of means, here's what we do. We obtain multiple samples, many samples, all with the same sample size. And all we care about from these samples is their mean. So we plot each of the means for each of these samples on a probability or frequency distribution. Okay. Now, if you do something like that, like we did with our coins, right? Even though coins have a dichotomous outcome, heads or tails, when we actually plotted the probability distribution, when we started taking multiple tosses into account, look what we came up with, a normal distribution. Let's look at something else. Let's look at the population of IQ scores of 10-year-olds. Okay. You have IQ scores for 1 million 10-year-olds. And you reach into that vat of 1 million 10-year-olds IQ scores. Imagine they're each written onto a slip of paper. And you pull out 64 of them. You take those 64 slips of paper with different IQ scores for different 10-year-olds, and you take the average. The average is 103.70. Now you take that number, and that number only, and you plot it onto your probability distribution. Throw it away. Throw all those slips of paper away. You're done with them. Now let's do the same thing again. Reach into that vat of slips of paper, pull out 64 again. And this time when you take the mean, you get 98.58. 98.58. So you plot that on your frequency distribution. Throw that away. Let's do it a third time. Reach into our vat of all these IQ scores, pull out 64 slips of paper, take the average of those 64 numbers, you get 100.11, very close to the mean this time. You plot that on the frequency distribution. Now you're going to do this again and again and again. Let's say you're going to do this about 1,000 times. You're going to have 1,000 samples by the end. From each one, you plotted the mean. If you do that, this normal curve is what you're going to get. This normal curve is what you're going to get. Okay. So let's look at this further. This is interesting so far. At least we hope so. Okay. So let's understand this whole concept a little bit more by watching this video together. And this is going to talk about the sampling distribution of means and how this leads into this normal curve for the sampling distribution of means based on the central limit theorem. Okay, so I'm going to switch our screen over for just a moment to this. And now I'm going to show you this video.
Somewhere in the fields, a brave ecologist is studying wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group, so he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population distribution is not normal to begin with? For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, the more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes, and the closer the mean of the sample gets to the true mean of the population. This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure. There is something very special about the normal distribution. Not only do many things we measure in biology follow a normal distribution, but it also crops up when we look at estimates of variables even when the variables themselves don't have a normal distribution, as we saw with dragon wings. Because of this, we can use the normal distribution to test ideas about the world even when the underlying variables don't follow a normal distribution. My name is Puthikrit Bhattacharya. This video was created by Shui Cho and brought to you by CreatureCast. Special thanks to Casey Dunn. For more stories, visit creaturecast.org.
Okay, so hopefully that video was helpful in understanding what we're talking about with the distribution of means and how it leads into the central limit theorem. You will notice that the link is right here, and I also put it at the end of the lecture in case you'd like to view it again, because it has a lot of information in just a short period of time. Okay, however, we will review it together. Okay. So the shape of the distribution of means, remember we collect all these means from all these different samples, will be approximately normal if you meet one of these two conditions. You don't have to meet both, just one. The sample size is 30 or greater, or the underlying distribution of the population of individuals is normal. Okay, so if you have a normal distribution, as we did with the rabbit weights, it doesn't matter if we have 30 in each group or not. If you have 20 or if you have 9, you're still going to get a normal distribution in the sampling distribution of means. However, in the case of the dragon wings, right, that was not normal, that was bimodal. Then we need our sample size to be at least 30 per group in order to get that normal sampling distribution of means. Okay. So this means, again, that the sampling distribution of means will be normal even if the distribution being sampled is not normal, as long as the sample size is large enough. And this is referred to as the central limit theorem. Sorry, the screen sharing just went a little crazy for a second, but I think we're back here. And I just am going to say again that this is referred to as the central limit theorem. Okay. So now we can actually look at another example that kind of displays how this works. Okay, so let's take a look at this example. Okay, so this is, as I mentioned, this is a dice experiment, okay? So let's start by just rolling 2 die. And you can see we're already getting into something that's starting to look a little bit normal. Now let's roll 5 die. Look how much more normal it looks. More normal, more narrow. And as we continue on, you can see that it continues to get more normal and more narrow. And if I actually roll the die, and I will do this in a moment to show you that this is what happens when you roll 25 die at a time, you will see that the distribution becomes more and more normal as we go on, more and more narrow. So we're doing this roll of 25 die 1,000 times together. And there you go. Look how close that is to the actual normal distribution. Not perfect, but very close. Okay, so now let's return to our slides. Okay, so let's continue talking about the sampling distribution of means. Here on the top, we have a nice population distribution. Notice the sample mean is 53, the variance is 49, and the standard deviation is 7. Now let's look at this distribution of means. Notice the mean is the same for our sampling distribution of means. It's still 53. But here, when we have this funny looking symbol, which is our variance for the sampling distribution of means, it's only 1.96 compared to 49. And the standard deviation of the sampling distribution of means is now 1.40 as compared to 7. How much narrower this is, right? And you can see it pictorially, but you can also tell it from the numbers. And then finally, on the bottom, we have a little sample that contributed 1 number to this distribution of means, the sampling distribution of means. Okay. So again, if we have a normal distribution to start with, which is what we're showing here, population distribution of scores, right? That's nice and normal. Even when we have a sampling distribution of means based on sample size 3, as long as we take enough of them, 1,000 or 10,000, we will get a more normal and more narrow sample. And even when our sample size is 9, just 9, look how narrow that gets and look how normal that is. Okay, All right. So now let's talk a little bit about the characteristics of the sampling distribution of means. Now we already sort of talked about this. I just didn't give you the exact formulas. So what is the mean of the sampling distribution of means? Okay, so how are we going to read this thing? The mean, the mu of X bar of the sampling distribution of means equals just our population mean. As easy as that. We don't have to do any math here, right? Just have to know the population mean, copy it over. That's the mean of the sampling distribution of means. Just like in the previous slide here, the 53 here matched the 53 in the distribution of means. Okay. Now, how do we get the variance of the sampling distribution of means? So again, sigma squared, remember, is variance of the X bar of the sampling distribution of means. How do we get that? We take our variance and we just divide by the sample size. We just divide by the sample size that we pulled. Okay. And then finally, we have the standard deviation of the sampling distribution of means, which is kind of a mouthful. So there's an abbreviation for this that I'd like you to get familiar with. It's called standard error of the mean, or SEM. You can ignore that little closed parenthesis there. It's just SEM. Okay. And how do we get that? Well, this is the standard deviation of the sampling distribution of means of the X bar equals standard deviation over square root of the sample size. Okay, so the formulas aren't bad. Once you can actually read through them and understand what they're saying, actually taking sigma squared over n, or more commonly taking sigma over the square root of n, is not a very in-depth formula. It's just a matter of getting the handle of what we're doing there. Okay. And so once again, we look back to our population of IQ scores in the 10-year-olds, and we remember how this frequency distribution came to be. And I point this out because I do want to show you how, whereas the mean is 100 for up here for our regular population of IQ scores, the mean is also 100 for the sampling distribution of means, whereas this is 16. Well, how do we get from 16 to 2? We take 16 over the square root of 64, right? That's what we're pulling for each sample size, 64. So we take 16 over the square root of 64, which is 16 over 8. 16 over 8 equals 2. Okay. So before we jump into confidence intervals, which we're about to jump into, I just want to note that the formula for variance and the formula for the variance for the sampling distribution of means and the formula for the standard error of the mean are really useful because the knowledge of sampling distributions is useful. For example, knowing the degree to which means from different samples would differ from each other and from the population mean gives you a sense of how close your particular sample mean is likely to be to the population mean. And the cool thing here is we don't need access to all of this population information to get there. The information is directly available from the sampling distribution. Okay. So the most common measure of how sample means differ from each other is called the standard deviation of the sampling distributions of the mean, or the standard error of the mean. So if all the samples were very close to the population mean, then the SEM, or standard error of the mean, would be small. If, on the other hand, the sample means varied considerably, the standard error of the mean would be large. So let's consider one specific example. Suppose your sample mean were 125, and you estimated that your standard error of the mean was 5. if you had a normal distribution, then you could be confident that your sample mean would be within 10 units of the population mean, since most of a normal distribution is within 2 standard deviations of the mean, right? 95% in there. Okay, so just something to think about. If that's a little bit much, as long as you got the part before that, I'm pretty happy. That's where we want to be. But I just wanted to share just a little bit more why this is so useful. Okay, all right. Now let's talk about confidence intervals. This is a range of values that we can be confident contain the true value of the population mean. So what is that? Okay, well, let's talk about a 95% confidence interval, which is one of the most popular confidence intervals. If we obtain many, many samples and construct confidence intervals for each of them, 95% of the confidence intervals will contain the population mean. So we can be 95% confident that our interval contains the population mean. And this translates to z-scores from negative 1.96 to 1.96 on the distribution of means. Okay, all right. So what does that imply for a 99% confidence interval? Well, that just translates to z-scores from negative 2.58 to 2.58 on the distribution of means. Okay, good. So what does all this mean though? Well, 1.96 and negative 1.96 might actually sound familiar to you because we actually used those numbers once before when we were talking about two-tailed distributions and putting 2.5% on each side. That's really the same thing that we're looking at here. Okay, well, let's look at an example to further understand this. Let's assume that our blue line in the center here is our true population mean. And let's say we conducted different studies with different samples, and each black dot is a sample mean. And we have 20 sample means for 20 studies. So for each sample mean, what we did is we built a sample confidence interval, a 95% confidence interval around the mean. That goes from one end of the pink line to the other end of the pink line. Those are our confidence intervals. So what will happen is if this is the true population mean and we pull these samples to try to get at the true population mean, when we look at the confidence interval, 95% or 19 of 20, which is 95%, of these will include the population mean. And look how that works. All but one, or 19 of 20 do. This one, this confidence interval, does not cross mu, does not cross the true population mean. All the other 19 do cross the blue line, do cross mu, do contain mu. So 95% of the time, our confidence interval contains the population mean, the true population mean, and we get it right. What happens 5% of the time? It lies outside. Okay. So how do we calculate a 95% confidence interval? Well, we'll get into this a little bit more next time, but for now, I just want to share with you the basics because we just saw this formula. Sigma over the square root of n, sigma over the square root of n. What does that stand for? That's our good old standard error of the mean. So if we take 1.96, which is our number of interest for a 95% confidence interval, multiply it by sigma over the square root of n, and then we take X bar and subtract that value, or X bar and add that value, we will get our edges for our 95% confidence interval. We will get our 2 points that we need. So the order of operations here, take the square root, then divide, then multiply, then subtract. So we're actually kind of working from right to left, even though I know it's more typical. We're used to working from left to right because we're following order of operations. We wind up working from bottom to top, right to left for these formulas. Okay. So I will encourage you to watch the central limit theorem video one more time just to make sure you have it. Feel free to review this lecture again, of course, but that is all I have for you today. Take care, stay well, and I'll talk to you next time.